So now in this video we're going to look at the NAND gate. We're going to have some demonstration circuits for that. One of them using the switch, one of them using the NPN bipolar junction transistor. I'll do a step-by-step build of these. And then the other one using the integrated circuit. And here's the part number up there. We'll talk about that in a little more detail. That's why I have these notes here. We'll talk about that later. For now, we're dealing with the NAND gate. Here is the schematic diagram. So the last video I did, we looked at the AND gate. So now we're at the NAND gate, which is basically a NOT gate and an AND gate in series. So here is the basic schematic symbol for the AND gate, but this little dot changes it to NAND gate, and this indicates that we're inverting the signal. And so if you look at the truth table, the output is the opposite of what it was with the AND gate. For the NAND gate, the output is going to be high if any of the inputs are low. We're only dealing with 2 inputs in this video, but there's integrated circuits and other things that have more inputs. But we're going to stick with 2. That's simplest. But if both of the inputs are high, then the output is going to be low. So we have the opposite of what we had with the AND gate. The signal is inverted. So let's begin with a switch demonstration circuit. So we will go to this schematic diagram and get the breadboard. There we go. So first let's put a switch on the board. I have this jumper there to indicate where to put one of the pins. So the switch connects, the top 2 pins are always connected, I should say. Bottom 2 pins are always connected. And these small ones fit nicely into the breadboard. And there we go. Got it right in there. So now we want to the top of the switch a 220 ohm resistor that goes directly to the positive side of the power supply. So now digital electronics, the integrated circuits especially, probably will operate at 5 volts. With the switch, voltage doesn't really matter. Whatever the switch can handle. And then of course the rest of the components. But the integrated circuits are a lot more delicate. So we have 220 ohm resistor. Now we're going to grab this LED. So I have a jumper up here. It's 1 space away from where the top pin for the switch is up there. The long lead, the anode, is this side of the schematic symbol. The short lead, the cathode, is this side where this dash is. With a lot of diodes, there's a black or different colored stripe where the cathode is. But the LEDs, we're dealing with a long lead for anode, short lead for cathode, as long as we didn't trim them. And the cathode also has a flat edge right there. So you should probably already know that by now if you're learning about NAND gates, but I thought I would cover it again. So right now we have a situation where the LED is normally going to be on. We got current going through the resistor and then across the switch, because these 2 pins are always connected to the long lead, the anode of the LED. Short lead, the cathode, goes directly to ground. So now we're going to build up the NAND part of it. So we need 2 inputs for this NAND. So we got 2 switches to simulate input, and got the other switch here, and we're going to plug it in. And again, top 2 pins are always connected, bottom 2 pins are always connected. We have to push the button to connect top to bottom. So now we will look at that now. So we got the LED on. As we said before, with the NAND gate, the LED is on if either or both outputs are low. So they're low right now, they're off. We can turn that one on or turn that one on. It's still on. So there we've covered the first 3 positions where one or both of them have low or are off. Now we'll turn both on. Now you see the LED turns off. So the basic principle is pretty simple for this type of NAND gate, and we are diverting the current. So when we press both switches, whatever energy gets through the resistor to push the current, gets to that top pin. When we press both of the switches, then it connects directly down this path to ground, which is a lot easier to go to than through the load, which is just an LED here. And that's the basic principle of a simple NAND gate circuit. And now we're going to build the transistor form of the circuit, and this is mostly a transistor video, but in this particular case we're going to use transistors as switches, and so the behavior of the circuit is going to be the exact same as the switch version. That's why I wanted to show this. It's a little less clear that that's what's happening, but really that's what's happening. These are going to be switches, just like the mechanical switches, but they'll be controlled by a signal, which is ultimately what you want with a NAND gate. And so we're using the 2N2222. These are actually 2N2222As, which are just slightly improved. They'll be behaving exactly the same in this circuit as a regular 2N2222. So flat side facing us, left pin is the emitter, middle pin is the base, and right pin is the collector. I've noticed that's the pin layout for any 2N transistor that I come across. So if it begins with 2N, you can pretty much guarantee this is emitter, base, and then collector. And then so emitter down here we're going to put at the bottom, so I'll turn it to the right for when it fits in the board. Base, middle pin, collector up there, top pin. And of course I'm putting the transistors in first. They have 3 pins that aren't very flexible, so usually I put them in, and then the other components I adapt to fit with them. So I'm going to put it one space below the gray jumper there, because again we're going to have the LED going to ground. LEDs, you can stretch out their pins and stuff, but I try not to. So we have the other transistor there. You can see the emitter of the top transistor connected directly to the collector of the bottom one. So again, we're going to face it towards us. Emitter bottom, base middle, collector on top now when the flat side's facing us. And we're going to plug the collector directly. Let's see if I can tilt this where we see better. There we go. Collector directly to emitter of the previous transistor. And of course the emitter for this one's going directly to ground. So now, before we do the 10 kilo ohm resistors, let's do our load first. Why not? We'll do the LED, and we're going to do the same thing. Long lead the anode where the collector of this transistor is. Short lead the cathode directly to ground. We have that gray jumper there. Let's make a little space, and there we go. And by the way, last time I tried to do this, it did not slide into there, but now it did. So I just moved it over once. Don't fight with a particular spot if you have other options. These boards can be finicky sometimes. So now, the other side, it's kind of the load, but we also have the resistor here. It's going to limit current through the LED and through the transistor. So 220 ohm, and we're going to put it where the collector here is, and then up here. Resistors are one of the most flexible components, probably the most flexible components when it comes to a breadboard. And oddly enough, there we go. It didn't really want to go in that time there. Hasn't been giving me problems yet, but there we go. You can see it's at the collector there. So now, at the base of both transistors, we have 10 kilo ohm resistors, and this should provide enough current through the transistors from a base to emitter to saturate them, to get them to fully conduct. And so let's do the top one first, and I want to go straight across because I'm going to use yellow jumpers to ultimately complete the circuit to give a signal. But there you can see we're putting it to the middle pin of the transistor there, and then this one, and so straight across we have this spot. So I'm going to angle it a little bit. Doesn't matter exactly where, but I want a jumper to be able to go straight across. So there we go. And now we have the same situation with the switch, where the LED has a direct path and it is on. Transistors are off. We can basically think of them as not even existing right now. It's just a resistor and an LED because they're not conducting. As far as the electricity is concerned, they don't really exist. They're just insulators, like the plastic on the board. So now we're going to take a jumper and give a positive signal to one of the transistors, and I'm not going to push it all the way in, but there we have a good enough connection. LED is still on, and then we'll connect the other one. Now you can see that it is off, so we gave both transistors a positive signal, and the LED, our output in this case, is off, and that's because, just like with the switches, we have a direct path to ground. So there's a little bit of current going through the base to emitter here, but it's enough to get the transistor to fully conduct. And then once it does, the current through this base to emitter now has a path through the transistor, which also allows this one to fully conduct. So they're both fully conducting, so it's an easier path from this point to ground than going through the LED, just like the switches. But of course, if we remove either one of them, that will cut off the path, either one or both of them, and it's on. So we have a fairly practical NAND gate here. So now we're gonna build the integrated circuit version of it, and this is mostly a transistor video, but this is really the next step to transistor circuits, is the integrated circuit. And so I figure I'll throw this in on here too. Plus I already had these from a kit that I got. So to begin with, this integrated circuit, it's the SN74HC00N. We'll go over what that means coming up, but basically what that part number tells you is that there's 4 2-input positive NAND gates. So you can see there, that's where the pins are for them. And so the first one is pin 1 through 3. As you can see there, it's a dual inline package. So you can see the divot there. Off to the left there is pin number 1, and you work your way down. So there's 14 total pins. We get to 7 down here, the ground, which I already have there. Then we jump over and we work our way up, so 8 to 14. And so I like that the output is right down there at the bottom for that one. So we're going to begin with our pull down resistors. So we're going to take 10 kilo ohm resistors, and because ultimately we're going to connect the pin directly to the positive rail, and so 10 kilo ohms is going to limit the current going from positive through the resistor to ground. We'll look at that coming up. And we just need the voltage at the pin. Current doesn't really matter in this with this integrated circuit at the inputs. And then so we'll take the other one and go to the other input directly to the negative rail. We cannot leave these pins floating. It'll pick up signals from the air or whatnot and falsely trigger like crazy. So we have to either have them connected directly to the positive rail or the negative rail. I'm going to say directly, but actually with a resistor, to either hold it low, which we're doing, or to hold it high if we put it to the positive rail. So in any case, we have it held low now. Let's attach our load. So I got a jumper down there, so I'll use a 1 kilo ohm resistor, 1000 ohm resistor, and that's because this is not intended to output much current. I think you're only supposed to output about 4 milliamps of current. And so if you need more current, output this to a transistor and use this to turn the transistor on and off and let the transistor handle the rest of the power. But that's a topic for a different video. We're going to stick with a really light load in this video. And of course we need the LED. This side will be more positive, so we put the anode there. Of course the ground's going to be the more negative side. It's the most negative part of the circuit. And there we go. So let's turn the power on. And now you can see, since it's a NAND gate, the output is high unless both inputs are high. Opposite of an AND gate. So we will just directly connect a jumper to the positive rail there, and we can put it to either input. Let's do this one first. You can see LED is still on. If I jump it over one, of course the LED is still on. So right now we're directly to the positive rail over to there. So the pin is getting a 5-volt signal there because the resistor is going to hardly absorb any of that energy. And so we'll take a blue jumper and plug it into the positive rail and do the same thing. Now we'll have 2 positive signals to the input, and of course the output goes off. Alright, so now that's really the end of the video. There's the part number written out for this particular integrated circuit. So I want to talk about what this part number is telling you. So first off, the most important thing is the 74 right here. It tells you it's a 7400 series component, and so the 74 indicates part of 74 series. The next 2 numbers, in this case we still have the 00, that indicates that it's a quad NAND gate there, whereas in the last video it said 08 right there. That let us know it was a quad AND gate. So these other letters are, or these letters I should say, are extra. So first let's start with the SN. Texas Instrument was the original maker of the 7400 series integrated circuits, and they had SN at the beginning. Other manufacturers may omit it. There may be no letter there. They might have other letters there, or they might still use the SN. You don't know. But this says Texas Instrument on it, so I know it was made by Texas Instrument. I also got it out of a Radio Shack kit that used the Texas Instrument integrated circuits. So in any case, let's move along. So HC is another couple letters inserted into the number there. So what that is, the HC means high speed, so it's an improved version of the 7400, and high speed for the H, and then CMOS for the C. And you can look up what that means. I'm just explaining in this video what that is. It may also say LS, and the reason why I added LS, which is low power and Schottky, is that both versions of these are really common on Amazon, where I buy my components, or a lot of my components. I'll also go to eBay too and stuff, but I buy a lot from Amazon. I have the free 2-day shipping, the Prime, and also they let me set up a storefront there where you can click the links from my link, and I'll get a percentage of what you spend. You won't pay extra, but I'll get a percentage for referring you basically. So these 2 forms are common on Amazon, so if you look up 7400 integrated circuit or whatnot, you'll probably either see HC version or LS version, which will be inserted there. So now the N, that is the packaging. So there's two dual inline packaging versions. The N is the plastic type, which we have here, and then there's also a molded type. I don't know what letter indicates that. You can find that out by looking on the data sheet, if that is available for this particular chip. I'm not sure, but for the data sheet, you just Google search this, put into Google this part number, and then data sheet, and this one's really easy. These 7400 series for a Texas Instrument, you just put the part number in. I get the data sheet every time within a link or 2. One of the easiest data sheets I've ever found. But in any case, the N is the P dip, so I made sure to write this out because I find dual inline package all the time. I don't think the dual inline package dip part's going to be hard, but with the P in front of it, I wanted to make sure I knew what that meant, and that meant plastic. If it says M dip, then it is molded dual inline package. I don't know how that looks different, but it's going to be a different packaging. It's still dual inline package though, which is the pins on both sides, dual inline packages, which fits into the breadboard pretty nicely. So for my purposes, I really like the dual inline packages. There's a bunch of other packages, and for Texas Instrument, you'll know which one by what the letter is on there. So that's important when you're buying them. Make sure you get the right package for what you're going to do. If you're going to put it in the breadboard, you're going to want the dual inline package for sure. And it doesn't matter if it's plastic or molded, but all I ever find is the plastic. So in any case, the data sheet's very important. Make sure you look that up. Wikipedia and other sources talk a lot about the 7400 series integrated circuits. There's more than 100, so as you can see here, we got this particular chip is 7400, even though it has letters in between them. The AND gate chip was 08, 7408, and so with just the 4 digits, because it's 74 series, we would only be able to have 100 different chips, because we got 00 up to 99. But they add more zeros after that for other integrated circuits. I don't think I have any myself, but I've seen them listed. And so there's more than 100, so you'll still have the 74 somewhere in the part number, but you'll have 3 or 4 digits instead of 2 to indicate what it is. And you just gotta Google the data sheet to see exactly what it is. So make sure you hit those data sheet hard. I'm just presenting general information to hopefully make it easier to understand the data sheet and how to use the component. I'm just learning how to use them myself. I'm not an expert. Plus, you should always go to the data sheet for the particular values of the component. You should never completely trust what anybody tells you. You go by the data sheet. And even the data sheet says it might not be 100% accurate usually. So, in any case, hopefully this was helpful. Thanks for watching.